Hello, my name is Dr. Seema Shah Fairbank, and in this video I will be presenting an introductory lesson on open channel hydraulics. After watching this video, you'll be able to differentiate pressurized pipe flow from open channel flow. In addition, you'll be able to define open channels in terms of geometric variables. You will need to put the channel geometry, width, depth, side slope, and or pipe diameter. Once those are inputted, you'll be able to calculate area, wetted perimeter, top width, hydraulic radius, and hydraulic diameter. Finally, you'll be able to identify the different flow types that are present in an open channel. Prior to the understanding of an open channel, it is key to compare the differences between pressurized systems versus open channel systems. A datum needs to be established. This is where all measurements are made from. The water within the pipe is moving from point 1 to point 2. The elevation head is measured from the datum to the center of the pipe, Z. Next, the pressure head is determined from the center of the pipe to a location above the pipe. Another way to think of pressure head is to assume that if there was no pressure, the pressure head would represent the actual water surface. That is why the slope of the pressure head is referred to as the hydraulic grade line, or HGL. The third term is referred to as the velocity head. It is measured from the hydraulic grade line to some distance above. The slope of the velocity head is referred to the energy grade line, or EGL. If you're interested in figuring out the energy at any given point, you will sum the elevation head, the pressure head, and the velocity head. The difference between the energy at point 1 and point 2 is the head loss within the system. On the other hand, an open channel elevation is measured from the datum to the bottom of the channel. The slope between point 1 and 2 is the bed slope. Next is the hydraulic grade line, which is depicted by the flow depth within the channel. The hydraulic grade line, or HGL, is also the water surface slope. Finally, the energy grade line occurs by adding in the velocity head. The EGL is also the friction slope. The difference from point 1 and 2 is the friction loss within an open channel. And the total energy at any point within the channel is the elevation head plus the depth of water plus the velocity head. Now that we have an understanding of the overall differences, we can discuss and understand the geometry of an open channel. Unlike a closed conduit, an open channel is a function of the topography. If you have a plan view of a river, you can cut a cross-section of that river, as shown AA. The cross-section view within the channel looks like the section view shown. Our section is section AA. We can identify the thaw wag of the channel as the lowest elevation within the channel, or the center line in the plan view. We can also see the left and right side of the channel. The reason it looks opposite is because in section view, water is going into the board, while in plan view, water is coming downstream, or coming from the top to the bottom. The cross-sectional area, A, is the hatched green section. The wetted perimeter, WP, or sometimes just P, is shown as the perimeter in contact with the channel. The top width is the width of the water at the top of the cross-section. With this information, you can determine the hydraulic radius, RH, and the hydraulic depth, DH, where the hydraulic radius is the ratio of area to wetted perimeter, and the hydraulic depth is the area to the top width. When you think of hydraulic radius in a channel, one way to think of it is if a channel is over 20 times, if the width of the channel is over 20 times the depth, the hydraulic radius is equal to the flow depth. Also, when you think of hydraulic depth, you can think of a channel looking rectangular, and the hydraulic depth represents the depth of flow in a rectangular channel. This slide shows the geometry of many common geometric shapes: rectangular, trapezoidal, triangular, and circular. The geometric information shown can also be found in most textbooks, online, or determined by you. For you to calculate these terms, you must know the depth, side slope, width, and/or diameter of an open channel. The final part of this video is to introduce you to various flows. Steady flow does not vary with time, while unsteady flow varies with time. The graphic shows how steady and unsteady flow differ as they refer to time. Uniform flow is when the flow rate and depth of flow does not change spatially. Uniform flow is steady, and also the slope of the bed. Water surface and friction slope are all parallel. In addition, the cross-sectional area will not change in space. The final category is non-uniform flow. It's broken into two categories, the first being gradually varied flow. The flow is steady, but the depth changes in space. While in rapidly varied flow, the flow depth changes abruptly. Examples include hydraulic jumps, steps, and contractions, to name a few. The flow in these cases are also steady. Now that you have an overall understanding of open channel hydraulics, we will further learn the different ways to calculate.